Okay. Again, this is not one of the suggested problems from this chapter, but it's very similar to the homework problem, problem 91 from chapter 3. In fact, we kind of attempted this during the class, but I screwed it up. I made the drawing too complicated. I'll try to make it a bit more clear this time. A boat is traveling where there's a current of 0.20 meters per second east. To avoid some offshore rocks, the boat must clear a buoy that's north-northeast 22.5 degrees and 3 kilometers away. The buoy's speed through still water is 2.1 meters per second. If the boat wants to pass the right side of the buoy by 0.15 kilometers, at what angle should the boat head? So here I screwed up because I tried to put two different diagrams on top of each other. You should not try to do that. That was a good lesson for me as well. So I'll put the velocities and the positions on separate graphs. So let's first start with the positions. This is our, let's say, north-south direction. We have a buoy that's half of right angle, and it's 3 kilometers away. But we want to actually clear this buoy by a further 0.15 kilometers. So we actually want to move in this direction. Right? This is what we want to do. Let's perhaps draw this with red. Okay? We want to move in that direction finally. So this is going to be our velocity of our boat with respect to the ground, to the shore, no, whatever you want to call it. It's not with respect to the water. This should be our final velocity. So we're going to head in a certain direction, but we are going to be heading this way. And let's call this angle theta. Sorry, I already have a theta. So let's call this angle alpha. Now, what can I say about this angle? I know this is 3 kilometers, and this is going to be actually two right triangles. So I want to reach this point. Okay? So I can call this maybe y1, why not? And call this one x1, and I can immediately write these distances because I know the hypotenuse, I know the angle that's given. So y1 is going to be 3 times cosine theta, whatever theta is, and x1 is going to be 3 times sine theta. Okay? Whereas if I call this final position I want to end up x2 is going to be 3 sine theta plus 0.15. Okay. Now I want to draw something separately for the velocities, though I used up a little bit too much space. So again, let's draw a north-south direction. Okay. So I'm going to go with a certain angle. I used alpha, let's call this beta. So this is going to be my velocity of the boat with respect to water. Okay. But I'm going to get drifted away by the current. So this is the velocity of the water with respect to ground, and I'll end up with some velocity of the boat with respect to ground. Note that this VBG is the sum of VBW plus VWG. And these are actually vectors, so let's put their arrows. These are not just magnitudes. And this angle is, of course, still alpha. It's just the same vector from over here. And the velocity of the boat with respect to water is given. So this thing over here is, excuse me, 2.1 meters per second, and the current is 0.2. So this is 0.2. This is 2.1. Okay? Now, again, I can write down some expressions for these angles. First of all, let's call this this thing Vy1, and you know this Vx1, and this is going to be Vx2. Say for the x component and y component of the velocity. So Vy1 is going to be 2.1 times cosine beta. Vx1 is going to be 2.1 sine beta, whereas Vx2 is going to be 2.1 sine beta plus 0.2. Okay. And we can also write that Vx2 divided by Vy1, Vy1, Vx2 divided by Vy1, yes. Vx2 divided by Vy1 is tangent alpha. Okay, and over here as well, we can say x2 divided by y1 is tangent alpha. So these are similar triangles. Now let's put them together. I kind of ran out of space, but I'm going to erase this. Hopefully it's not going to be needed anymore. Okay. But I have just one more step. I'll just set these two equal to each other. So x23 sine theta plus 0.15 by 3 cosine theta is equal to Vx2 2.1 sine beta plus 0.2 over 2.1 cosine beta. These are equal to each other, and I'm looking for beta. How would you solve this? You could multiply this by that. And remember, I know theta, so this is just a number. The left-hand side is just a number. So you can move this to the other side. Take the squares, and then use the fact that cosine square beta is 1 minus sine square beta. So you're going to get a quadratic equation in sine beta, and you can solve for it, and then use arc sine. It's a little bit convoluted, but this actually solves the problem. And honestly, I don't see a way to solve this more cleanly. Okay? But one of the important things that I messed up during class was that I tried to put everything on the same diagram. Then it becomes very confusing. You know, you don't want to put alpha, beta, and theta on the same graph, especially is beta larger than or smaller than theta. That leads to some confusion. But apart from that, it's just similar triangles. Okay? If you draw two separate graphs and put the positions in one, put the velocities in the other, and write down their components, these come out, these things come out, and from the larger triangles in both figures, you can say that the tangent of this angle is going to, you can also say that these are just similar triangles and set these equal to each other immediately, but maybe it helps to see that they are both equal to tangent theta, the opposite divided by adjacent.